So this is a chapter from the overall AIML in I don't know whatever it was called. I forgot. Let me see. This was a book that we just went through very rapidly from Mercator Oceans, Copernicus, State of the Planet, Ocean Prediction, and so on. It was called Ocean Prediction, Present Status, and State of the Art. So one of the chapters is about how AIML is going to play a role in ocean forecasting. This says crafting the future, machine learning for ocean forecasting. I'm only going to expand on this particular chapter. The others we just briefly touched on because they are, very important in an operational technical way, but for podcast as a whole, this is a more exciting new direction, so I'm going to focus a little on this. Artificial intelligence and machine learning are accelerating research in our system science with huge potential for impact and challenges in ocean prediction. Such algorithms are being deployed on different aspects of the forecasting workflow with the aim of improving its speed and scale. We discussed this a lot already for atmosphere, ocean, coupled systems, Earth system, climate predictions, and so on. They include pattern classification and anomaly detection, regression and diagnostics, and state prediction from nowcasting to synoptic, subseasonal, and seasonal forecasting. Synoptic is typically, let's say, day 1 to 10. Subseasonal is week 2 to 4, and seasonal is, of course, beyond a season to interannual time scales. This brief review emphasizes scientific machine learning methods that have the capacity to embed domain knowledge. So if you are doing ocean forecasting, then you need to know specific things about the ocean, very different than the atmosphere and can be different than the coupled system as well. And the request for information is also very different. So this ensures interpretability through causal explanation to be robust and reliable. And also we want the review to look at how to involve effectively the high dimensional statistical methods supporting multi-scale and multi-physics simulations aimed at improving parameterization. We already talked about how AIML is helping climate models and atmospheric models to improve parameterizations, to replace submodules, and maybe even hybrid modeling will get more and more popular, where you're taking a physics model and let's say a dynamic core of a climate model or atmospheric model and a data-driven physics model, and coupling them together to computational efficiency and so on and so forth. Okay. And overall, this should also help us with intelligent automation as well as decision support. An overview of recent numerical developments is discussed, highlighting the importance of fully data-driven ocean models for future expansion of ocean forecasting capabilities. I'm going to be brief, but it does touch on some things at a basic level that we'll read off because they can be important overall in terms of pedagogy. I keep looking at my phone because I have movers coming in soon. I have to leave this place. Okay. Give me a second. This idiot, I gave him the location, but he lost it. So, okay, so sorry about that interruption. Let's go back to reading a bit of the opening text. Research into applications of AI and ML in ocean atmospheric climate sciences has accelerated. So let's skip the introductory material and just jump to basic research needs for scientific machine learning is being published in books and reports already. This is from the US Department of Energy report. So this emphasizes 6 elements of SciML, which is scientific machine learning. So ML approaches that incorporate domain knowledge such as physical principles, symmetries, constraints, expert feedback, and computational simulations and formal uncertainties. ML approaches that are interpretable such that a user's confidence in ML-based model predictions may be bolstered by causal explanations based on a user's domain knowledge, which means AI can be AIML I drink a lot of water, but somehow when I start talking, I begin to have dry throat, very high humidity. So, nonetheless, AIML can be a black box, and many times companies that sell you tools, AIML-based tools, want to give you a black box so that they hold the licensing and the ownership, etc. So, on the other hand, you want to have interpretable products, interpretable tools, because you want to know why it produced the answer it produced. So AIML has to not only accelerate things and improve parameterizations, it also has to improve process understanding and causal inferences so that we know what it is doing. ML approaches that are robust and reliable as a prerequisite for making high stakes and high regret decisions are a part of the SciML, sorry. We have discussed the difference between AI and ML. ML is going deeper in terms of layers and details compared to AI, which is doing, basic emulation of how our brain works, for example, in terms of audio-visual cues and interpretations, patterns, etc. And interpretable and explainable are concepts I have discussed elsewhere as well. Interpretable is exactly what steps happened, what steps AIML took before giving you the answer, whereas explainable means you have some output, then you have a separate model that explains what happened without giving you all the details. So it's a bit complicated. We also need ML approaches that are data intensive, i.e. that ingest high-dimensional, noisy and uncertain input data which contain complex structures and which require statistical and probabilistic methods to deal with ill-conditioning, non-uniqueness and overfitting. When you do interpolation, given the data, you can do a lot of things to make sure that your fit is perfect, but as soon as you extrapolate to one step, let's say for prediction, things can fall apart because you have overfitted the curves just to get a good answer. ML approaches that enhance modeling and simulation to support multi-scale and multi-physics simulations in terms of improved model parameterization or model acceleration, computational efficiency are also critical elements of SciML. And finally, ML approaches to support intelligent automation and decision support, which can range from quality control to application-oriented post-processing workflows. Arguably, all these criteria are fundamental to the uses of ML in ocean prediction as well, even though they were not specifically written for ocean prediction. Jumping ahead, there is a review by Reichstein, which is useful to distinguish different categories of ML applications, and those are classification and anomaly detection, which is concerned with, for example, finding extreme event patterns, or the classification of important structures or regimes, clustering kind of things. Regression, second one, regression, which is concerned with the state reconstruction of important state variables, parameters, or diagnostics or metrics from available data, which is normal statistical methods, but AIML can do much better in terms of the layers that may be hidden. And thirdly, we also need ML applications for state prediction, ranging from nowcasting to operational forecasting and sub-seasonal to seasonal prediction. Nowcasting is just next minute, next few minutes, next hour, and so on. There's no strict difference, but generally nowcasting also needs to happen quickly. And if your model takes, if you are trying to make a 6-hour prediction and your model integration to make the prediction takes 12 hours, then obviously you are not going to get 6-hour prediction done in time. But AIML is going to be very critical in doing that. But other issues in terms of S2S or sub-seasonal to seasonal predictions. Okay, a comprehensive collection of review articles on deep learning in earth sciences is Camps, Walls et al. 2021, covering algorithmic foundations and examples of all three categories. So we'll obviously read this. I think I've already recorded it, but I'll make sure. Okay. So Touching on these state predictions, so the workflow of operational ocean prediction largely follows that of numerical weather prediction, NWP, which has been in business for now for more than half a century. Its core engine is data assimilation framework consisting of physical models, so complex algorithm for basically you have numerical solutions of Navier-Stokes equations with energy and thermodynamics, and you have data assimilation because weather prediction is an initial value problem, so you need to give it information of what the real atmosphere and ocean look like at this moment so that you can integrate forward and make the prediction. So data assimilation is kind of very has a lot of similarities to what AIML tries to do, but in a different purpose. You're trying to blend data into models to initialize the model to look like the real world, and so on. And there are a lot of issues, a lot of methods associated with them as well. So there are other references that show that machine learning approaches hold the prospect for accelerating various elements of data assimilation workflow. They are summarized briefly here, but I'll skip them. I won't go into all the details. This is a very nice chapter, but the approach I take is to give you enough of the most salient points and not go through the whole thing unless that's actually necessary based on the context. So soft AI versus hard AI are also used, so you can let's see, do I need to read that? So you have submodel replacements, parameterizations, and one of the most important applications has been to use AI to downscale, let's say, dynamical forecast. Dynamical forecast model may be giving you a forecast at order 10 kilometers, but you need often heat wave flood information at neighborhood scales, and with data and model forecast, you can use AI to downscale to those scales as well. Okay, so second one, or under state prediction, you have hybrid physics ML models, enhancing forecast models, and data assimilation with ML algorithms. We discussed this already a little bit in the application of AIML in Earth Sciences and other podcasts beforehand. So basically, as we said, when we say hybrid physics and machine learning models, I hope I didn't say mixed layer. Machine learning models, radiation module in the climate system, for example, or physics is like convection, clouds, etc., as opposed to the dynamical core, which is solving momentum and how winds are affecting things and so on and so forth. So the combination seems to be giving good results in terms of accelerating the computational speeds as well as improving accuracy and interpretability. Anything you do with AIML has to have interpretability. Okay, so exciting efforts are underway to apply machine learning to replace conventional functional representation of subgrid scale turbulent oceanic processes. So that's the improvement of parameterizations. Mixing is a big black box well, it's not a black box, but we struggle with it on how to do it right. The data is never enough, and we don't always know exactly how mixing happens. We have many theories based on data. We keep collecting data on turbulence, microstructures, and so on, but we still remain quite deficient in understanding and modeling the mixing. So AIML is beginning to help. Okay, equation discovery has proven successful to infer the functional forms of such subgrid scale ocean parameterization schemes. Longer list of related efforts exists, so similar to the other things we have discussed in the other categories where how AIML is helping. So ocean is a little bit behind. Computer vision, speech recognition, image recognition have gone very far in the non-climate fields, but climate fields have posed many challenges because of the system's complexity, non-linearity, uncertainties, and so on. Ocean is a little bit behind compared to weather prediction and climate prediction. Okay, so there are also improved parameterizations that are used for bias correction or analysis. Using data, rapid progress is expected in all these fields in the coming years. Second important application of hybrid approaches of using physics based ML versus dynamic course, let's say. This is the desire to replace specific numerical algorithms within the partial differential equation based models, or dynamic models is a better word. So there are many such efforts already going forward. The underlying idea of these is to eventually be able to generate code. The underlying idea is to eventually able to generate code for the derivative of the physical model, in particular the adjoint model that enables efficient online or full model learning of the model parameters or neural network weights. Well, many technical words there. Adjoint model is something that integrates backward and says, to get the right answer, where do you have to be in terms of, let's say, the correct initial condition or water mass, and many details there, but you can look up adjoint model in my data simulation discussion elsewhere. Okay, this third one, purely data driven models replacing numerical simulations with surrogate models. So you may end up replacing, let's say, convection in the ocean with some sort of a ML algorithm that is embedded into a dynamic model. So wherever you don't have first principle equations to solve numerically to get solutions, you will use mixing. For example, we write equations and we have parameters in them, so ML can either replace it or improve the parameters. Deterministic applications in weather predictions, we have already talked about this. When we said deterministic, we meant that there is only one realization, but we know that small errors or differences with the real world in terms of initial conditions can produce very different solutions in terms of forecast for the next few hours to a few days, let's say. And numerical models typically perturb the initial conditions in various ways to produce a range of solutions. We call them ensembles because Mother Nature will take one of them. So your idea is to surround the realization as much as possible, so that you have a probabilistic prediction, because you can't be very deterministic at that level. So, but generating ensembles from AIML is going on now as well. Okay. Let's read some particular details here of the methods. We mentioned these before, but this provides some basics that are worth reading. Convolutional neural networks, CNNs, we mentioned a lot. Perhaps among the first serious endeavors using ML for emulating weather forecast models have been the CNNs. CNNs use a mathematical operation called convolution to compress information, learning features or patterns in the input. So you are dealing with volume of data, velocity, speed at which they keep accumulating and coming at you, variety of data, and the problem with veracity, quality control, etc., especially with physical constraints for AIML, because they may produce something without knowing the physics that may be not physically correct, like let's say it starts snowing in a desert, or snowing in Singapore, let's say. Singapore is not expected to get snow anytime soon unless we have a snowball Earth episode and so on. So CNNs worry about these sorts of things. CNNs have been used to create coupled atmosphere-ocean emulator, which produces stable climate for 1,000-year periods and appears to be competitive with many CMIP6 models. Emulators are basically offline models, let's say, which know what the model does, and then it keeps doing emulations as opposed to integrated model simulations, so they can be much faster. Running 1,000-year periods on a dynamical CMIP6 model, especially with high resolution, can take forever, but emulator can do it incredibly fast. But then you have to be sure that it also is looking similar to the dynamic models when you compare them over common periods. Graph neural networks, among the leading emulators for the medium range weather forecast is the work by Lam et al. Based on graph neural networks, the GraphCast model was trained on atmospheric reanalysis data to produce autoregressive forecasts for up to 10 days. Autoregressive means it makes a forecast, uses that forecast for the next level integration of forecast. So it can keep on doing this and keep going for 10 days, which is remarkable because it does well. But remember, it's using reanalysis products, which are blended data model products as for training, which gives it a bit of artificial skill, because in the real world you are doing data simulation, which is not exactly reanalysis. They are analysis and reanalysis, so some details there. Transformers, these have been revolutionary in the other AIML fields, such as natural language processing and image recognition and generation that I mentioned. They serve as the backbone of some of the leading atmospheric emulators, including Pangu Weather and Fengwu. So many models are out there now being used for real-world applications. Fourier neural operators, FNOs, have been designed to move toward mesh-independent operators using Fourier bases. So FourCastNet, F-O-U-R CastNet, is based on a variant called adaptive FNO, Fourier neural operator, sorry. Another variant is spherical FNO, seeks to take advantage of the spherical geometry and the underlying symmetries, could be hemispheric, could be zonal, in representing operator kernels for global scale applications. AIML can use symmetries to basically do, reduce the computations. If something looks exactly symmetric, then you do it here and apply it there, okay, approximately. Recurrent neural networks, so including long-term, short-term LSTM, long short-term memory LSTM, and reservoir computing. So these are technical terms. I'm obviously being incredibly brief and just reading the text because I'm not really a technical expert. I use these for doing things, applications. It's like driving a car. You are not an automobile engineer, but you must know enough about the car to drive it. Especially if you break down, you should at least be able to open the hood and see, maybe you can figure out something like a disconnected battery or something. Okay, anyway. Okay, so recurrent neural networks, RNNs, are well suited for sequential data processing such as time series. Among special cases of RNNs, LSTM, long short-term memory networks, use a special type of neuron that keeps track of previous inputs, so short-term memory, and are especially useful for predicting time series with memory, such as the case for the atmosphere and ocean. So when you do image recognition, speech recognition, memory may not be a big issue unless you are doing a video analysis to forecast. Like let's say you're looking at people moving, and then you want to see where they went after some time, but you don't have a video, then you want to use AIML to do that. But in the climate system, especially ocean, memory is very critical because ocean has high heat capacity, very deep, so it has all the memory in the Earth system comes mostly from the ocean or glaciers, right? So that's the idea there. Reservoir computing, another method based on RNNs with a pool of interconnected neurons forming the reservoirs. This is particularly well adapted to the emulation of time series. Okay, so just try to get an intuitive sense. Probabilistic approaches, generative models. So generative models basically train themselves to use the available data to keep going. Most examples sketched in section 2.2.1 that we looked at describe emulators that are trained to be deterministic forecast models. So just think of it as a single realization of a forecast. Recent developments in ML have considered generative frameworks, i.e. models that are designed to be probabilistic, which means you get multiple realizations. Such frameworks would involve variational autoencoders, generative adversarial networks, GAN, and diffusion models. Technical terms, so let's not worry about it. Here we note that GAN can suffer from a lack of sample diversity. So when you want to do auto-coding and so on to keep using generative methods to produce continued integration, let's say, then the training data has to have enough samples. If you have, let's say, a regime shift coming up and that's not in the data, then GAN can miss it or misrepresent it. So They are notoriously challenging to train, requiring a careful setup to avoid training instabilities as well. Moreover, in recent years, diffusion models have started to outperform GANs in image classification. For these reasons, diffusion models have become popular in generative modeling despite their relatively high computational cost. Recent examples of diffusion models include GenCast. Finally, we note a very recently developed technique, diffusion, which is a generative framework that aims to reduce computational cost of diffusion modeling by encoding the temporal evolution expected in physical systems into the generative process. So everything gets developed in, let's say, the real world for image processing, analyzing big data of consumer behaviors, etc., or speech recognition for, tracking terrorists and so on. But when you try to bring it into a system science, especially oceanography, you have to worry about what the additional requirements are in terms of memory and so on. Before feeding these, you cannot just translate directly generative processes from other fields into climate science, so you need to train them to be mindful of the specificities of our field, right? Physics-informed machine learning. Results of purely data-driven solutions may potentially produce meaningless output, as the training strategy of a neural network is to just minimize a mathematical loss function, for example, the mean squared error, L2 norm, between the prediction and the original target. It doesn't care, it will just hammer a minimization of root mean squared error, let's say, without worrying about causal inferences or even Bayesian inferences or physical constraints. Similar issues, for example, producing overly blurred output may arise with other choices of the loss function, such as an L1 norm. An evolution of this approach, like a regression model, an evolution of this approach is to include some physical constraint in the loss function in order to force ML algorithms to produce more consistent outputs, such as the Navier-Stokes equation. So you have deep learning ML doing its thing, and then you put a physical layer to make sure that physical constraints are satisfied, like no snow in Singapore for now. Okay. This class of methods is known as physical informed neural networks, PIN. However, the performance of PINs for extrapolation remains subject to debate, so these are still being tried out. Recently, another approach which tries to solve differential equations using neural networks is under development. Although this method is mostly developed for other physical fields, the methodology and knowledge can be applied to ocean modeling. So there is the non-climate field applications that are learning things. We're applying them to climate, weather and climate forecast, let's say even in a coupled system, and then the ocean application. So we are behind all those. Applications in ocean surface state forecasting. The previous examples mostly are limited to weather prediction and computational fluid dynamics in a few cases. Now we turn our attention to applications in the context of predicting ocean surface properties like waves, temperatures, etc. They include the use of multi-layer perceptrons and long short-term memories for surface wave prediction, surface wave current interaction, forecasting, storm surge forecasting, sea surface temperature prediction via deep learning, and the use of neural networks for accelerating resonant nonlinear wave-wave interactions in an ocean surface wave model, so that can lead to rogue waves which can have serious impacts, regional to coastal sea level predictions, ocean color mapping, statistical downscaling, and so on. Other applications include estimating ocean surface circulation and predicting dissolved oxygens across dissolved oxygen across scales. So just a run through the examples. Let's see how long I am, because I got interrupted there. How many more slides do I have? Oh, I'm almost at the end, so let's just run through it. Okay. I'm being very brief and being very fast as well, but you get the idea. I'm just trying to give you the lay of the land about AIML, what's it's being used and where it can go in the ocean prediction application. Mixed machine learning based ocean circulation prediction is going on as well. They rely on the use of data obtained from high fidelity model simulations as training data sets. So like using reanalysis, these data sets are very expensive to generate, but you can use them and then run emulator models for repeated simulation, repeated what if scenarios, let's say. So these can be limited in temporal ranges because integration can take long. Imagine running a 0.1 degree ocean model, global scale, especially if you add ecosystems, chemistry, and so on. Carbon cycle can take forever. Okay, so these also require vast amounts of storage and are challenging to query. You know, when you have a query system, you want to ask a question and it has to do its internal large language model computing and spit out an answer. Cloud-based solutions are the most promising approach to ubiquitous data access and analysis capabilities close to the data. So cloud-based solutions is basically where we have discussed this a little bit already. There was a chapter in this book on that. Big companies like Google, Amazon, Microsoft, etc. provide cloud computing services where they can store the data, run your computations, and you are just using them, kind of not having to own and manage your own power supply and high performance computing, etc. etc. They may also do optimizations in terms of GPUs and so on. So within the realm of ML applications for ocean forecasting, progress has been somewhat limited. Jumping ahead, another challenge presents the extension of ML applications to seasonal, interannual, and multi-decadal, i.e. climate time scale applications. Here, the increased need for models or invariant operators, so physics-based or surrogates, to conserve fundamental properties such as mass, energy, momentum, and active tracers, puts severe demands on ML approaches. Arguably, as these approaches increasingly incorporate physical knowledge, they will converge to the realm of classical inverse methods. Inverse methods basically solve something like AX equal B, where A is a vector, B is, let's say, a linear operator, and so you're looking for solutions. So if you have a lot of data, let's say on currents and temperatures, can you back out the most well-constrained heat transports associated with these currents and temperature distributions? That's kind of the inverse modeling. Has a lot of applications. Benchmarking forecast models. Obviously, you want to constrain the forecast models. Typically, forecasts are done with dynamical models, and then there is a obviously calibration validation happens, but each time you make forecasts, then you have to go back and see how well you did, and there are various metrics for skill scores, and you have to understand what skills are, temperature is good, but maybe salinity is not so good, or mix layer is good, but thermocline is not good, mixing, etc. So lots of details, but obviously ML models also have to do these. Benchmarks comprise common data sets, open source evaluation workflows, and common evaluation metrics, so you can compare multiple models. Like in CMIP 6, we do coupled model intercomparisons. Similar benchmarking efforts in ML-driven ocean circulation and surface wave forecasting will be equally important to advance the field and establish standardized evaluation metrics. Coming closer, the role for surrogate models in digital twins. This is the last section. The concept of digital twins, DTs, is rapidly gaining traction within the ocean science community and earth system science more broadly. You understand intuitively what that means. On a computer, you have the full ocean model in a digital form, so that you can do tests. If somebody spills oil here, where will it go? The digital twin can do the simulation, and then you can go to the real ocean and try to set up your measures to contain it, or where the storm is going, which ships are in its way. So digital twins can be incredibly useful for quickly doing simulations of what will happen with something that's about to happen in the real world. Okay, because of the differing view of what constitutes a digital twin in recent literature, we here adopt and emphasize the definition from National Academy's report. I think that's what this is called, NASEM. I should read. Anyway, you can look it up. A set of virtual information constructs that mimics the structure, context, and behavior of an individual unique physical asset, or a group of physical assets is dynamically updated with data from its physical twin throughout its life cycle and informs the decisions that realize value. A digital twin is highly dynamical, mimicking the time evolution of its physical asset via advanced simulation and emulation capabilities, and it's updated by ingesting vast amounts of observational data for diverse types, and it enables what-if queries and multiple realizations of the system to support prediction of responses to the physical assets to hypothetical perturbations with quantified uncertainty. So if you are looking at a fisheries system and you want to manage it, you can look in the digital twin how the quotas can be set, or how the fishery is going to be affected by climate like El Nino, or warming, deoxygenation, acidification, etc. Okay, coming to the close, virtually all aspects of ocean forecasting and ML opportunities therein may be viewed through the digital twin lens, from the need to generate high fidelity simulations or digital representations, ingesting, i.e. assimilating large and heterogeneous data streams, and the development of fast surrogates or emulators to either accelerate simulations or provide comprehensive uncertainty estimates to the generation of diagnostic data that create value for possibly rapid decision support. So when we say heterogeneous data, we talked before about velocity of data at which it's coming, volume of data growing tremendously when you combine satellites, in situ observations, and model outputs, let's say, or reanalysis, and also variety of data, because you are getting biophysical data, acoustic data, chemical data, human activity data, and so on and so forth. So the system has to smoothly synthesize all of them together to extract the information. Okay, exciting times. If you're young, you are at a good time to learn a lot and be a part of the big solutions as well. Okay, let's leave it here.